All right, so the next thing that we're talking about is rate laws. So we've talked about calculating rates, right? So what do we do with those? I mean, what's the purpose of calculating rates? And the answer is to make these things that we call rate laws. A rate law just gives us the relationship between the concentration and how fast a reaction will go. So think about what we've been doing. We've been measuring concentrations and seeing how they change with time, right? Or and with and so now what we're going to do is look at how the concentration can be used to predict the reaction rate. Okay, so what do they look like? Well, let's say this is our reaction that's right here, right? A plus 2B goes to 3C. A rate law might look, for example, like this. So this reaction rate, right, is equal to K times the concentration of, let's say, A times B. It might look like that. And so there are different parts to the equation. There's the reaction rates, right? RR is still the reaction rate, not rate. There's, oops, sorry. There's these brackets like this, right? Like this is the concentration A. And then there's brackets like this. That's concentration B. But then there's this K, and this is known as the rate constant. It's the proportionality constant. Because you can always say the rate is proportional to A, and the rate is proportional to B, or rate is proportional to A times B. You can say stuff like that. Remember, if you're going to make it an equality, then typically throw in a proportionality constant. And so in this case, K is that value, rate constant. Now, here's the deal. There are some common, some mathematical forms that we have for rate laws, because it turns out, like the one that I did for you here, this is kind of the sort of hopefully the simplest one. Kind of turns out there's possibilities that it looks like this. And I'm going to drop the brackets so I don't have to draw them all. It could look like that. And so now this, right, is used to represent that. And that's just a simplifying thing to make it go a little faster for us. Or it could look like this. Let's do B instead. And remember, this would be B to the first, right? So we haven't said that, but there's implied ones on these. Because if they were zeros, right, anything raised to the 0 power, let's say I take A to the 0 power, anything raised to the 0 power is 1. Okay, so having said that, how do you know which one it is, right? How do you know what the relationship is? And the actual answer just comes down to this. You have to do an experiment. In order to figure out what the orders are, okay, figuring out the orders, remember those orders, this is the powers, right? In order to figure those out, you just have to do an experiment and find out. And so we call these like part of the different parts, right? Like the exponents are called orders, just like they are in math. So we're looking for the reactant orders or the reaction orders in order to figure out what the rate law is. And so we could say they're 0 order, that means something, right? First order is what I'm showing you here. And then second order is what I'm showing you for, oh gosh, how did I do that? The second order is what I'm showing you for here. Now, when we say something is 0 order, simply that means, right, its concentration, regardless of what it is, doesn't affect the rate of the reaction. That's a 0 order reactant. So the common ones, it turns out the orders are 0, 1, and 2, but you can have halves, like you can have a half order, you can have a 1.5 order, you can have a 2/3 order, you can have fractions like that too. We will not encounter any of the weird fractions, but a half maybe you'll occasionally run into. So these are what rate laws are, and we determine them experimentally, okay? So, just some important ideas before we get into the calculations. The rate laws are always determined from data. The type of data that we usually use are called initial rate data. So remember when I talked about initial rate data, initial rate um, for a reaction earlier? We put the reactants in, we start the reaction often by mixing, and then we look to see what that initial concentration change is over time. Okay, and so we usually change the initial concentration, and we measure the rate at one concentration, and then we change the concentration, and then we remeasure the rate. Okay, so we do this to get the orders, but the idea is you have to change the concentration and measure the rate change, right, in order to figure out what the order is. And basically, it's lather, rinse, repeat. You know the thing it says on a shampoo bottle, right? Um, if you have two reactants, you got to do at least two experiments for each. Well, actually, you can get away with fewer than that. But let's say if you have two reactants, then you would need four experiments. That's kind of the simple way to think about it. Um, if you had four reactants, then you have to do 8 experiments. So these things are all interrelated, but the easiest way to do these experiments is leave one concentration the same at the beginning of the reaction and then change the concentration of another. And then you can see very clearly what that one reactant is doing. Okay? So we can use this change. It's really like the ratio of the reaction rate change versus concentration change to figure out what the orders are in the rate law. So let's take, and I think, yeah, I used to show all the work on the slide, but I think it's easier for me to explain it if I don't do it that way. And I'll use some different colors to help you, but here's what we're going to do. We want to figure out how the rate changes for A. Okay, so how are we going to do that? Well, clearly you have to change the concentration for A, right? So if you're looking at this data here, right, you have 3 experiments. This is like the bare minimum number of experiments. Like I said, there would be 4 for 2, but the bare minimum is actually 3, and you'll see how we do this. Which experiments does A change in? So the way this is set up, right, is for experiments 1 and 3. And then the other thing that needs to be true is these are equal. Does that make sense, right? That way I'm only looking at the change in one variable. Now this is my initial reaction rate over here. So in order to get the rate law, and I'm going to show you 2 ways to do this. I have a favorite way to do it, and then I have the way that I'm supposed to teach it, so I'll show you that first. Anyways, so what we're going to do is we're going to say for reaction rate, right, 3, and I'm doing 3 over 1 because if you notice this, the way I type these out, it shows up that 16 is bigger than 4. So I'm going to do reaction rate 3 over reaction rate 1. Okay, so that's going to be 16.0 times 10 to the minus 5, and then 4.0 times 10 to the minus 5. And then this is what I'm going to do, right? I'm going to say it like this. This is equal to, I maybe should show you something else first, but I'll just show you what it's equal to. It's equal to this. And I'm cheating. This is the way I like to do it and not the way the book does it. This is the concentration for reaction rate of A, for reaction rate 3, right? And then for reaction rate 1, the concentration is 0.100. And this is going to be raised to a power n. That's what I'm trying to determine, what that power n is. Okay, so then I'm going to take and I'll divide this out, and this will come out to be 4.0 is equal to 2 to the n. Now, here's the tricky thing. You have to figure out what n is. Now, in this case, you could probably figure it out just by looking at it. Like, what's the exponent of 2 that gives you 4? And it turns out that that's 2, right? So n is equal to 2 in this case. So we've just figured out what the order is for A. So I know that my reaction rate law, okay, is going to be K times A to the second, but I don't know what happens with B yet, okay? So this is just to figure out A, which is usually, like I like to do them in order. You don't have to, but I'd like to do them in order. Now what I'm going to do is I need to look for the set of conditions, okay, where the concentration of B changes but A doesn't. Okay, so that's actually, so this is experiments 1 and 3 up here, and the experiments that we're looking for are experiments 1 and 2. B doubles, right? B goes from like 0. It goes here. So let me change my colors now so that I can. Let's see. I'll do, and I think this will show up okay. Blue. Yeah, that'll show up good. So I'm going to do reaction rate 2 over reaction rate 1. And that's going to be equal to, right? Let's see, 4.0 times 10 to the minus fifth divided by 4.0 times 10 to the minus fifth. Oh, by the way, I didn't write units here because they cancel out, okay? So then what will happen is that's going to actually equal 1, but this is also equal to this. And then I'll show you how I get this. So B is 0.2 for experiment 2 and 0.10 for experiment 1, and that's to the nth power. So here we go. We're going to say this is equal to 1, right? Is equal to 2 to the n. And this should look familiar to you because, right? And I'm comparing these two and these two. Sorry, I meant to draw that in there. Because that means n must be 0. So what I know is that the rate law looks like this based on my data. Now, the output of this then is just that reaction rate is equal to K times A squared. When I left the brackets, I'll put them back in. So this is the easy way to do it. So let me explain to you what some of these things are. This, right, is the rate ratio. And this is the concentration ratio. And so the concentration ratio is always raised to an exponent that you need to find out. Now, we would say that this reaction is 0 order. And then I'll show you how that I got to that equation. 0 order in B, and second order in A, right? Overall second order. Oh, that's right. I'll do it like I did over. And so basically the overall order is just what you get when you add those two together. So if it had been 1 and 1, it would have still been 2, right? Or if it had been 1 and 0, it would have been first order overall. And then the orders are just the exponents. And so B not being dependent on concentration, the rate not being dependent on the concentration of B means that that one is 0 order. Okay, so good question is, where does this come from? Okay, so next slide, right? This was my proposed rate law here. Oh, pen's not working. Oh, there it goes. Proposed rate law. It's that the reaction rate is equal to K times A to the M and B to the N. And it could have been X and Y, but I find people are too stuck on X and Y and other letters need a chance, right? So this is what I'm writing. Reaction rate. This is the general rate law is what it is. It includes all the cases. So reaction rate 3, right, is equal to K times A, right, to the M, and react times B. And you know what? I'm going to get rid of the brackets just to make it easier to write. To the M and then B to the N like this. But reaction rate 1, let's say, if this is what I was doing mathematically, is k times a to the m, right, and b to the n. Now this would be a3 and b3 and a1 and b1 like that. So, so the way we did this experiment, right? The way we did our calculations is actually we did this. We divided the two equations out because I didn't want to deal with this. And this is sort of a standard sciencey math trick. You divide constants out so you don't have to deal with them. And then you hopefully can come back and figure out what those constants are. In fact, that's what we're going to do with our other data here in just a second. And I have to show you some other math tricks as well. But we can divide that out. And so this is going to be equal to a3 to the m, b3 to the n, divided by, right, a1 to the m, and b1 to the m, like that. Now, or n, sorry. And then I'm going to do a little math magic. I'm going to separate those two and get them to be ratios of concentration. So the little math magic is I can do this. A3 over A1 to the m, because I pulled the exponent out, which you can do, times, then it's B3 to the over B1 to the n, like this. Okay, so now let's go back and look at experiments 3 and 1 and look at what the numbers were. Okay, so A3 is 0.2 and A1 was 0.1 and B was 0.1 in both. Okay, so in other words, and I'm looking right here, right? A in 1 was 0.1 and in 3 is 0.2. And we won't worry about this part over here for now, but we'll come back to that. And then it's 0.1 and 0.1. So what does this equation do when you have that, right? So what that means is this is going to be 0.200 molar like this, and 0.100 molar like that. This is all raised to the m power times, and then remember it was 0.100 molar for both. And then n here. And what happens? That cancels out. And now you have 1 to the n power, and then you don't have to worry about solving for n at the same time you're solving for m because you made it constant. Okay, and that's the reason why making one of those values, one of those concentrations, constant, is that it drops out of this equation and then it's easier to solve. Now, when we put the other side of the equation, there's R3 over R1, right? Then when we do that, then what we have is R3 over R1. That was equal to 16, I believe, 0.0 times 10 to the minus fifth molarity units per second divided by 4.0 times 10 to the minus fifth molarity units per second. Again, units cancel out, and now we're left with the number 4.0 is equal to this. Like that. Okay? And this is where we got to when we did, whoa, that was weird. This is where we got to when we did this. Okay? And what I did was made B go away by, in the experiment, this is part of experimental design, being able to hold one constant. Now, people can't always do that, right? So the analysis has to be more complicated at some level, but it's not here. So they can hold one of these constant, it goes away, and then you're only dealing with what's changing. That was the beauty of experiments 1 and 2 as well. In that case, A disappeared and B stayed, and we were able to calculate the order for B here because A went away. So really what we're dealing with, this isn't really N up here, that really should have been M. Or no, this one isn't N up here, it really should have been M, but I kind of just spaced out when I did it. So okay, hopefully that made some sense. Now there's a little bit more tragedy here that has to be talked about, and it's the math that you have to remember, because I know you know how to do it. If you're in this class, you've done this probably dozens of times, but it was dozens of times years ago. Okay, so let's deal with it. It's the use of logs to solve for exponents. So I have this equation. It looks like this: 4.0, right, is equal to 2 to the n. How do you get in? Well, in this case, we kind of just said, I chose an example where it was easy to see that it was 2. And oftentimes people will set up problems so that the answers are clear to see. But how do you solve it? The way you do it is you use logs. And you can either use base 10 logs or you can use natural logs. I'm a natural log kind of guy. So I will take the natural log of both sides. Like this, and the right hand side becomes this, because the exponent you can multiply it by, times, right, natural log, times the natural log of 2. And now you can solve it algebraically. N is equal to the natural log of 4.0, and this was actually, I think, 2.0 as well, but we'll just do it like it's natural log of 2. And then we can pull out my handy dandy calculator. The reason I say handy dandy calculator is if you were ever forced to watch Blue's Clues as a child, yeah, that's what they say. You know, the handy dandy, and it was something. So, so we're gonna take 4, and we're gonna take the natural log of 4, which is on this calculator down here on the left, divided by, right, the natural log of 2, and I have to put the 2 and then the natural log, and then I'll hit equals, and that's equal to 2. Okay? So this is 2. Now, you could have done that. You could have solved that using some identities and stuff, and it would have been easy, but we're not doing that, okay? Right, so that's the idea. This is how you go about solving these problems when the ratios aren't pretty. If they're not 2 to 1, what is 1 1/4 to 1 or something like that? Then what do you do with that? You have to use this method of using logs to solve for it. And there's a little bit on the math review worksheet that we're doing, but mostly it's depending on you to remember how to do it, okay? Okay, so what we need to do next, because we haven't done it yet, we haven't calculated the rate constant for this reaction yet. And so what we're going to do is we're going to calculate K, right, for this reaction. Here's the thing. There's 3 sets of data, and students often get confused, like, well, which one am I supposed to use? If they don't tell you which one to use any. Because remember, it's a constant. So it should be the same for every reaction, give or take a little bit of, experimental noise. Now, in this case, it's exactly the same. Generally, it's not exactly the same, but I'll show you how to do the calculation. So I know that the rate law, I've put it up here, is this, right? So I can say reaction rate, so that's going to be RR, right, is equal to K times A squared, and then I'm going to rearrange this because I want to find K. So I'll have K is equal to RR over A squared, and then I just plug numbers in. Now, well, let me just do it. So then I'll do experiment 1, that's 4.0, right, times 10 to the minus 5th, and the units are molarity per second. And here it's important that we put the units in because we're going to calculate something that needs to have units. So it's important that we put the units in. And so I'm going to divide that by 0.1, yeah, 00 times 10 to the minus, just 0.001 molar. But it's squared, right? So it's like this. So when I do that calculation, I need to move this control out of the way. I'll keep running into it. When I do that calculation, that'll come out to be 4.0 times 10 to the minus 5th molarity per second divided by 0.0100 molarity squared, okay? And then that'll come out to be 4.0 times 10 to the, I'm just doing the exponent math in my head. minus third. And then I'm going to end up with this funny unit, 1 over molarity times second. And this is typical of a second order rate law, wherever, it's second order overall, that you have molarity in the bottom because you're dividing by molarity here. That's the only way it can be, so that when you multiply it out, you get these units out as the answer. So when you're trying to figure out what the units are, really you just can put the units in and divide it out and see what the units come out to. That's what most people actually do. Instead of doing it all at the same time, they think about what the units will be, they do the calculation, and then they just write the units. Okay, so yeah, you could get the units for K simply by dividing molarity per second, which is what reaction rate is in, by the value for that, which would end up being molarity squared because it's a second order reactant. Okay,